So previously we were looking at the derivative simply as a value, the slope of a tangent line at a point. Like I said, we want to open this up. We want to make this more general. We want to make the derivative something that's really more versatile than just that. And so that's how we're going to now treat the derivative as a function. Okay, we're going to see how we do this. So let's just define the derivative of f at x. So the derivative of f at any point x. That's what the difference here, not a specific value a like before. Okay, so this derivative, this definition, the derivative of f at x is given by, okay, f prime of x is what we're seeing here. So that's a little prime symbol. And that's what we say, f prime of x. That's one notation. We'll look at other notations in a minute. Okay, equals the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so that's just like what we were looking at before, except instead of a specific a, we're looking at a more generic x. Okay, provided the limit exists. And we'll have to get into that in a little bit of why might this limit not exist. Okay, so a bunch of things that we can talk about here. Let me say a few things first. Notice the derivative is actually a limit. It's not the limit of the function, it's the limit of this difference quotient. Okay, so it's not the limit of f itself, it's the limit of this difference quotient, fx plus h minus f of x over h. But it is still a limit, so when we're looking at it, we still have the same ideas of limits behind it. Okay. So let's mention a few other things. Notice that f prime of x, so f prime of x is actually a new function. All right, we had a function f of x, and then we've gone to another function f prime of x. So we come up with a new function. So it's interesting that we start with a function, we do something, apply this derivative, and we get a new function. All right, so the original function f of x is said to be differentiable at x if the derivative exists at x. That's just defining the term differentiable. Means you can get the derivative at that point. And just to go from a point to an interval, a function f of x is said to be differentiable on an interval if it is differentiable at every point in the interval. All right, so that's just to generalize the term. Now, it's not like you actually look at every point in an interval. We're going to have ways of making the determination of where we would look for places where it's not differentiable. And we'll be able to say that some functions are differentiable in lots of places, and we know where to look for lack of differentiability. All right. So now the derivative is so common, it's so important in many fields, mathematics, physics, economics, biology, chemistry. Lots of, virtually everything can use a derivative because everything that involves change often has a derivative associated with it. So you will see a lot of different versions of the derivative for that reason, but also because of the way that the derivative was originally constructed. All right. Basically, two mathematicians, Newton and Leibniz, were working on calculus at the same time and came up with slightly different notations. So what we referred to before as the prime, f prime of x, was from Newton. And that was Newton's idea for the notation of the derivative. So what we're saying is, if we're talking about y equals f of x, if that's the function or graph that we're describing. All of these are different ways that we could describe the derivative. So we've looked at f prime of x. Sometimes we would just suppress the of x, notation and just say f prime. Or sometimes we would just say y prime, because this is really y as f of x. So then the other way is to use this d dx notation, and that's due to Leibniz. Okay, this is Leibniz notation, and it has its strengths too. So both are nice for different reasons. The prime notation is often shorter and quicker. The Leibniz notation is a little more formal and does give you a little bit more flexibility in terms of being very clear about what the variable in our derivative is. Because when we're saying derivative, we're really saying derivative with respect to a certain variable. We're being a little sloppy about that now because we're only using x right now, but we'll get into other variables as well. So that's the Leibniz notation. So if we had a function f, we can talk about the derivative as df dx or d dx of f of x. This makes it clear that what we're doing is we're doing this operation called the derivative on the function f of x, okay, which is sometimes shortened by just df dx. Or again, if we want to use y instead, we might just say dy dx. And then there are other notations. This is really related to calling it a differential operator. So basically the derivative is doing an operation to a function. So sometimes it's denoted as the derivative with the respect to the variable x of y, the function y, or f of x, whichever you want in there. So we have to be flexible in going back and forth between some of these notations. And you'll see sometimes we're a little even sloppy and switch using the notations within one problem. It's probably not a great idea, but I think it's okay.